Um, I will today share with you about the recent development of a new microscopy for charge carrier mapping of photo device materials, which is used for photocatalyst, solar cells, and so on. So my name is Kenji Katayama from Chuo University, and this has been recently published in Journal of Chemical Physics, and please refer to this for further information. So here's the content of this talk. First, I'm going to talk about the research target, and then move on to the development of the new microscopy, which is the two topics. One is about the hardware things, and the other is statistical data analysis things in the last two topics. So first, let's move on to the research targets. So here the target of our materials, which is a semiconductor particulate films. And of course, TiO2 is one of the most famous photocatalytic materials. And also there are many semiconductor materials which is made of particles like zinc oxide, iron oxide, copper oxide, and then sulfur material too. And these kind of materials have been used in solar devices recently. For example, in photocatalysis, where if you have organic dirty materials on the wall or surface, and then one part of here is coated by photocatalysis using the sunlight energy, it can decompose the organic materials into the water and CO2. And the other application is water splitting, where the sunlight energy is used for the split the water into the oxygen and hydrogen. And also in many solar devices, oxide layers are used for charge collection or transport, or even the charge accumulation layer. And they are now getting a big industry and very important. So when we think about the key factors for photo devices in terms of the mechanism, first here is a photocatalyst. Here's a TiO2 case. When the light is illuminated, electron is excited and the holes are generated. And electron is used for reduction reaction, and holes are used for the oxidation reaction. And in the case of water splitting, this electron is used for the generation of hydrogen, and holes are used for the oxygen generation. And in the case of solar cells, you are going to add extra molecules or some material for light absorption. And when the light is illuminated, electron is excited, and they are transferred to the conduction band and also going into the circuit. And on the other hand, holes are transferred in the opposite way to get current as a final output. So in any cases for the photo devices, the photo excitation happen, and these electrons and holes are generated, and somehow we need to stop to recombine and disappear of these electrons and holes, because we want to use these electrons and holes. And also the other important part thing is that we need to extract these electrons and holes. So to utilize these charge carriers efficiently, the charge separation method is important. We have to separate electrons and holes. And to understand this process, we need to know the properties of the lifetime and the transport properties of electrons and the holes. Okay. So if these are the real problems, it's not a big deal actually, because physical property of lifetime of charge carriers and mobility of charge carriers, we can measure it. But the real problem is a little bit different. So when we think about the particulate film, meaning the films made of the particles, and if you are trying to make a 1 centimeter device, photo devices, if you are using the 10 nanometer particles in 1 centimeter, even for one dimensional, you need a million of particles on the horizontal direction. So there are many interfaces, defects, and cracks in this film. So that's a real problem. And you can see that this is TiO2 nanoparticulate film. And if you look into that on the various spatial scale, you can find many different types of defects or cracks and also aggregates. So is this a real problem? Yes, because looking at here, if you use a single crystalline TiO2, here's the whatever signal is after photoexcitation, the charge carriers were observed during the decay. Right? So in the case of the single crystal TiO2, it decayed with a single exponential decay because the vertical axis is logarithmic, meaning that the charge carrier is basically a homogeneous type of single type of the charge carriers. However, once it is changed to the particulate film, you can observe that after photoexcitation, charge carrier decayed on the order of nanosecond, microsecond, and 100 microsecond, and millisecond, or even second order. So suddenly, there are many various decay processes, meaning that various type of decay charge carriers inside the film. That's a problem. So this is because these kind of dirty films we are using, and the key is the charge carrier behavior is totally different between the crystal and the particulate film. So in a sense, there are many types of charge carriers, but you don't know which charge carriers are important. So in a kind of like, in this kind of mess, you have to find out which type of charge carriers are really working as for photocatalytic or target reactions, right? So what we need to understand is here, so as I mentioned, there are many multiple types of defects. That makes most of the charge carriers are just trapped to the defect state. And also due to many different type of defects, the lifetime of charge carriers ranged for multiple orders. So in some cases, charges might be mobile, right? So what happened when the light is illuminated here is the charge carriers are not generated homogeneously, but locally generated like this. And then they might move around. So to understand these properties of charge carriers, we need to develop a new type of the analytical method to obtain the lifetime and the transport properties. So we need a spatial temporal information of charge decay is necessary.